Okay, so good afternoon all of you. So today our topic is about deletion operation in heap. Okay, so the deletion operation in heap can be done based on few steps here. Okay, so what is the first step? We have to delete the maximum from the tree. We have to delete the maximum from the tree. So that means in the heap, say suppose if you have fruits like this. So which would be the first one to remove? The topmost one. So similarly here in the max heap whatever we have, so deletion operation means always it's the root only. So that is nothing but root. So deletion operation means nothing but deleting the root because that is the value what we have maximum. Okay. So after we delete this, say suppose if this is deleted, so imagine that this root is deleted. So in its place, so after deletion the remaining will be two disjoint subtrees. The remaining will be two disjoint subtrees. But what is heap? What is the heap property? So it should maintain complete binary tree and also max heap. Okay. So these properties should be maintained. So in order to do that, what we are doing, maybe randomly among this, we cannot keep any one of the element in the root. But what element we can keep? So here, if you see the array representation of this, so this is at index 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6 and 7, 6. So 10 is here, 9, 8, 7, 3, 4, 6. Okay? So the heap whatever we are going to take is a perfect max heap tree. Okay, so from that the deletion operation can be done by taking out the max element. Okay, deletion operation in heap means root only because root only will have maximum. Okay, so here when I am deleting this, which one will occupy its place so that these two conditions are satisfied. See, randomly I cannot say 1 will occupy, 2 will occupy, 3 will occupy, all this will be wrong. Occupying the last element into the first node. This process will maintain complete binary tree structure. Is it not so? So when we are doing like this, so what's happening here? So 6 here, 9, 8, 7, 3, 4, 6 and an empty slot. Okay, so when we are doing this, is it not a complete binary tree? Because the sequence is maintained from 1 to 7. So here, when this is happening, so what exactly will happen? So first at 1, so the last node will be inserted. So here it will be 6, here it will be 9, and 8, 7, 3, 4, and this will be empty. Okay, so among several elements when one is deleted, so the last one whatever is there is going to occupy the front position. So by doing this, we are maintaining complete binary tree property. Okay, so what about max heap? What about max heap property? It is not satisfied. Max heap property is not satisfied. So in order to do that, what exactly we have to do? So we have to adjust. So adjust with what? Adjust the elements of n minus 1 remaining elements. Anyway, 1 is deleted. So we have 1 to 6 elements only. Instead of 1 to 7, 1 to 6 are left over. 1 is over. So among 6, we have to adjust that and again we have to make it a max heap. And then again we can delete the topmost element. So is the procedure clear? Is the procedure clear? Yes, now please confirm. I'll tell you the example now.
Um,
Yes, ma'am.
Ma'am, can you repeat again, ma'am?
So I'm telling you with an example you see here. So if at all the array structure for the given tree is given like this: 1, 2, 3, 4, 5, 6 and 7. So 10, 9, 8, 7, 3, 4, 6. So deletion means first element will be deleted. So consider that deleted element into some x. Okay, remove the topmost element. Topmost element means say this is array A. Okay, so array of 1. So and index 1, whatever is there. So delete this element and you keep it some x value. Okay, so once this is deleted, so first delete the maximum, that is nothing but the root. After you delete that, what we have to do? In the array, whatever is the last element, so last element is going to be replaced into the first root. So now, how many we will have? 6, 9, 8, 7, 3, 4. 1, 2, 3, 4, 5, 6. So the 7th row is there, the element is moved to the first index. So that is what we are doing. Replace last element in the array in root position. Okay. So then what we have to do? So these are n elements. In first whatever we took, that was n element. After deleting an element, how many this will become? N minus 1. So is this n minus 1 element? So if you redraw this tree structure, so what is moving on to the root? Last index in the array, 7th index in the array, that element will be moved into the root. So now how we can redraw this? So 6, 9, 8, 7, and then 3, and then 4. Okay, so by removing the last element and substituting into the root, so this process is maintaining in order to maintain the property of complete binary tree. Is it not? 1, 2, 3,
Ma'am,
4, 5, 6. Yes, ma'am.
sometime your voice is not coming, ma'am.
Why? It's the same thing, ma'am. I'm in college now. Is it okay? Okay, I'll hold my mic like this. Is it okay now?
Yeah, okay, ma'am.
Okay. So here, when root is deleted, so who has to occupy its place? So the last index value in the array will be occupying the root's position. So by making last index value to occupy the root position, so what property we are maintaining? We are maintaining the property of complete binary tree. Okay? By substituting last element in the array into the root node, complete binary tree property is set. So once we give like this, the tree structure can be redrawn like this and the array can be rewritten like this. Okay? But now, what is the second property? Is it a max heap? Is it a max heap? So among all the elements, the root is having maximum? No. So what we have to do? So in order to make it into max heap, so you need to going to call the algorithm called as adjust for the array starting from 1 to n minus 1 element. So initially it was n. So after deleting 1 it will be n minus 1. Is it not so? Okay, I'll tell you this adjust procedure now. Till here the first two steps are there here. Delete the maximum, what is the root, and then replace the last element in the root node, and then we have to adjust. So this third step I am going to tell now. Okay, so what exactly we are going to adjust? So here 6, 9, 8, 7, 3 and 4. Okay. So when the tree structure is like this, so the adjust algorithm what exactly it will do? So is going to do from the last parent. Okay. So here, what are the indices? 1, 2, 3, 4, 5, 6. So n is equal to 6. So the last parent means anyway these are leaf nodes. So last parent you will get by doing n by 2. So that is 3. So starting at root node 3, so we are going to compare. Since there is only one element here, so since there is no other element, was between the children it will compare. So only one children, that is maximum 80. And then compare with its root. Is root value greater than 4? Yes, so we don't change. So the next parent is 2. Okay, so compare its children. Among 7 and 3, which is maximum? 7 is maximum. And among 7 and 9, which is maximum? 9 is maximum. So no need of swapping. Okay, so after that, what is the next parent? That is 1. What are its children? 9 and 8. Among 9 and 8, which is maximum? 9 is greater. So whichever is greater, compare that with the root. So if the root value is lesser than its children maximum value, they have to be swapped. So now we can rewrite this 9, 6, 8, 7, 3 and 4. So once these two are swapped, now is this greater than its children? So among these two again check which is greater. 7 is greater. So again check these two, 6 and 7. So this need to be swapped. So what it has to be done? 9, 7, 6, 3, 8 and 4. So is it a heap? Is it a heap now? The root node is having maximum compared to its descendants. 7 is maximum compared to its children. 8 is maximum compared to its children. So now it is adjusted. Now it is adjusted. Is this clear till here, all of you?
Ma'am, can you repeat, ma'am?
Yeah, please concentrate here. So lot many things are there which are interrelated in our terminology. So that's why even I am taking maximum time and again and repeating. So deletion operation. So this is the last time I am repeating. Please concentrate all of you. So the deletion operation, these steps you remember first. So deletion means, so among the fruits heap, so which can be taken first, which is at the topmost level, as of now. Okay, so
Yes,
similarly, in the heap, we are going to take the topmost element. So that is nothing but root. Deletion in heap means it's root only. Why? Because that is the maximum element. Okay, so when you delete that, so which one will occupy its place? The last element in an array will be occupying the root place. Why we are doing so? Why only the last element in the array is occupying the root's place? Because to maintain the complete binary tree property. If last one is moving to first, then the sequence again it will be, say suppose you have 7 elements in an array. If one is deleted, remaining 6. So what could be the complete binary tree sequence? 1 to 6 only, right? Okay, so in order to maintain the complete binary tree property, at first index whatever is deleted, in its place for last one, it is going to occupy the first place. Replace the last element of the array in its root. Okay, so by doing this, we are maintaining the complete binary tree property. And after doing that, is it a max heap? Maximum it may not be. So in order to convert into a max heap, what we have to do? We have to readjust the element. For that, we are going to call adjust algorithm. So what is adjust with n minus 1 elements. Among n, 1 is already deleted. Remaining are n minus 1 elements. And these n minus 1 elements need to be adjusted in order to form max heap. Okay? So that adjustment procedure I am telling you here. Again I will tell you later also. In tomorrow's class adjust procedure I will tell you. But example you just listen. Okay? So in this example, so when the root is deleted, so the last node whatever was 6 is occupying its parent's place. I hope here it is clear the first step, second step. The last node in the tree structure is occupying the root node. Till here is this clear?
Yes, ma'am.
Okay. So after that what we are exactly doing? Okay. So this tree whatever we got is having complete binary tree property satisfied. But it's not a heap. How? The root node is not the maximum when compared to its descendants. So what we have to do? We have to readjust all these elements in a heap so that it becomes a max heap. So in order to do that what we are doing is, so in adjust procedure, in adjust algorithm, first exactly what we are going to do is parent, last parent. Parent means what? A node which is having children is called parent. Yes or no? A node having children is called as parent. But when I say last parent means will 6, the node at index 6, is it a parent? It is a leaf node. And this one, node at index 5, it is a leaf node. Node at index 4, it is a leaf node. But node at third index is a parent. So in the tree structure, so last parent means, so if n is the index, so n by 2 will give you the last parent in the tree. Okay, so here n is now 6. So 6 by 2 means 3. So from index 3 we have to go. So first we will do for last parent. Here is it not 3? This you understood?
Yes, ma'am.
Okay, so last parent 3 means, so what we have to do? You have to take last parent. First compare among their children. So there is only one child. So I say among children, that is the only maximum. When one is there, maximum of them. So that itself will be the maximum. So 4 is maximum. So after that you compare with its parent. 8 and 4. Is parent maximum here?
Yes, ma'am.
Yeah, yes. So, no need of swapping. Okay. So, last parent is this. So, next parent it will be 2. So, we come to 2 node. So, here what we are going to do? First compare with its children. Which is maximum, 7 or 3?
7.
7 is maximum. So, okay, so I am at this point. So, now among children, whichever is maximum, that element you compare with the root node. Among 7 and 9 is maximum. Anyway, it is at root node. So, no need of swapping also. Is that clear?
Yes, ma'am.
Okay. So, next parent we have done it 3, 2, now it is 1. So at root node 1, so first compare among the children. 9 and 8, which is maximum? 9 is maximum. So among the children, whichever is maximum, so you keep that maximum value and with that value you compare the value at root node. So 6 and 9, which is maximum?
9.
9 is maximum. So we need to swap. So when we swap these two, so I have rewritten here. So 9 maximum? 7 is maximum. So you swap this. So when you swap, so 7 is going to its root position and 6 is going to come to the leaf position. So now, if you see, 9 is greater than all its descendants, 7 is greater than its descendants, 8 is greater than its descendants. Is this clear?
Yes, ma'am.
So that is what the adjustment procedure. Okay, so that is what the adjustment procedure what we have learned. So similarly here, once this is done, so what is the next element to be deleted? Next element to be deleted, quickly we do.
Maximum.
9 is to be deleted. So in 9th place, which have to occupy?
4.
Last index value. So 4 will occupy. So when 4 is occupied, what will happen? So when 4 is occupying, so 4, 7, 8, 6, 3. Okay. So 4 it has been moved to the first position. So when you have redrawn, this is the thing what we are getting. So by making the last element to occupy the root node, so what does that mean? We are maintaining the complete binary tree property. But after replacing that, is it a max heap? 4 is at root. Okay, no. So again we have to adjust. Okay, so in order to adjust, what we'll do? Last parent you should find. So what is the last parent now? So n by 2. What is n now? 1, 2, 3, 4, 5. Okay, 5 by 2. So that means 2. So last parent is 2. Yes or no? So now
Yes, ma'am.
compare these two. Among 6 and 3, which is greater? 6 is greater. So among 6 and 7, which is greater? 7 is greater. So 7 is in its place. So what is the next parent? Root node. So what are its children? 7 and 8. Which is greater? 8 is greater.
8.
So now they compare this. So 4 and 8. 8 is greater. So what will now happen? We have to swap this. So 8, 7, 4, 6, 3. So now this is the adjustment. And again what to delete? Maximum will be deleted and the last node will be occupied. So like this the procedure of deletion will be done until it is one element. Okay, again I will be covering this in some other topics completely. For now you just remember these points. Okay, so let me tell you the algorithm.